Hey, everybody. So today I'm going to be walking you through a very famous paper in econometrics that is available in your Canvas module, Treatment Effects Part 2. You'll notice that again this week we don't have a collab assignment. The reason for that in part is because I want to walk you through this paper and I'm going to show you some collab because I simulated the paper. But a big reason is I want you to be thinking about your project still because those deadlines are coming up relatively soon. Please reach out to me to chat about your project. The majority of students have done that for now, but I would still love to talk to each of you about what your plans are for your project, just so we can brainstorm. I can provide early feedback because that tends to be useful. But let's get into this lecture. So I've already mentioned this paper in previous lectures and sent it to you. It's a very famous paper in terms of estimating treatment effects in econometrics. It's called Estimating the Payoff to Schooling Using Vietnam Era Draft Lottery, which is basically what we call a natural experiment. And these are two very famous econometricians that whose names show up in a wide variety of data science and econometrics type things, especially in terms of this idea of estimating treatment effects. So let's go. I just summarized this paper in these notes for you. So Angrist and Krueger, 1992, what they do in this paper is they estimate the return to schooling. So this is obviously a pretty old paper at this point, but still incredibly famous because of the technique it uses. So I just want to walk you through the logic of that paper. And then, because I think having this clear sort of complete example is useful on a lot of the things that they need to think about. So their goal is to estimate the importantly, causal effect of education on earnings while addressing endogeneity. So especially ability bias and selection bias. So we've already mentioned those two things. Basically, ability bias is a specific type of selection bias. Ability bias means people who have higher inert ability or inherent ability are more likely to go to school and are more likely to earn higher earnings. So that, to the extent that's true, we're going to get too high of estimates of returns to schooling because of that selection amongst high ability into more schooling. So research design, basically between 1970 and 1973, the US men's draft priority was assigned randomly based on birth dates in the Vietnam era, what's called the draft lottery. So men with low lottery numbers, high draft risk. So if you got a low number, that means you are at high risk of being in the draft because basically you get random numbers. And then based on the needs of the military, they would say a number like 50. Everybody below that number would be drafted. So that's why having a low number increased the probability of being drafted. Well, then that led to a behavioral reaction. People understood this, and men with relatively low draft numbers would choose to go to college because they might be able to get a draft deferment by choosing to go to college. So this led to exogenous variation in the amount of schooling, basically, because that choice was essentially random through selection of the in the draft. So then, of course, you already know that based on that, lottery numbers can essentially be an instrument. They're relevant because we just explained that they're correlated with schooling. Low draft lottery numbers, higher likelihood of going to school. So that means they're correlated theoretically. And then also, they're exogenous because schooling and earnings probably don't impact draft lottery numbers because they are random by design. So the structural equation, that means the equation, this is like when we're doing a system of equations, one way to refer to those as the structural equation. So this is fundamentally the equation that the goal is to estimate this equation. So earnings as a function of years of schooling, SI, and of veteran status, because they propose specifically in the paper that maybe veteran status impacts earnings too, and that would be an issue. So, because draft lottery numbers are also, of course, correlated with being a veteran. If you have a low draft lottery number, you're more likely to have been drafted and be a veteran. That might impact earnings. That's going to be important to think about. So then, of course, covariates that might also impact earnings that we want to control for. So this is just a set of control variables. That's why it's written as a vector right here. X prime beta, and beta is a vector. I'm sorry, X prime is a matrix. X is a matrix. X prime is just it's transpose. So epsilon, of course, is just our error term. Now we expect that we have correlation between S and epsilon as a result of ability bias, just if we were to go to collect data on years of schooling and earnings. So that, of course, is the nature of our endogeneity issue. So then, of course, as you know, we're going to perform two-stage least squares. I guess you didn't know that, but that's what they do in the paper. Maybe you didn't know. Maybe you did know that if you checked out the paper. So the first stage equation is we, of course, want to predict our years of schooling. So in years of schooling, now we can say, well, Z is draft lottery-based instruments. Delta is the effect of a veteran status on schooling. So maybe being a veteran impacts schooling itself. Alpha is the effect of draft risk on schooling. So again, Z is the draft lottery-based set of instruments. Alpha then is the impact of those on schooling. So, and I think this should actually be a Z prime, sorry. Because that's going to be a Z is a matrix too, and alpha is a vector of parameters. So, of course, and then the underlying logic, men facing higher draft risk if they have low lottery numbers tend to obtain more schooling. Because again, it's like if I have a low draft lottery number, high likelihood of being drafted, one way to get out of that would be getting more schooling. And notice that that choice is independent of ability because there's no ability parameter in the probability of being drafted or getting a low draft lottery number. So of course, then we predict those numbers. And then in the second stage, our rho hat, what we actually care about is just covariance, schooling, this our earnings schooling hat over variance schooling hat, which is just, again, our standard simple regression parameter. And then they also later estimate models where they treat both schooling and veteran status as endogenous in that paper as sort of a robustness check because they want to see, hey, is veteran status itself actually endogenous? And they come up and you can read about the reasons why veteran status itself may not even be endogenous because maybe you have a weird correlation between, yeah, this person has a low draft lottery number, but they were already planning on being in the military or something like that. Because the draft lottery numbers are based on birth dates. And so you don't necessarily know everything about the people with those birth dates by just using the draft lottery numbers. We're making some assumptions about the people who received that draft lottery number. So now the identification logic. So the word identification comes up a lot here. I'm sure I've mentioned it in previous lectures. So that word comes from the goal is to identify the effect of schooling on earnings. So the identification logic is what logic is being implied to say, yes, we indeed have identified that specific parameter of interest. Well, lottery numbers affect education, but not earnings directly, is one of the assumptions. And we refer to that as the exclusion restriction. In the past, I referred to that as sort of the exogeneity versus relevance. Those are the two things we want. That remains to be true. The exclusion restriction refers to the exogeneity of the instrument. And basically, the idea here is that the draft lottery numbers only impact schooling. Well, sorry, only impact earnings through their impact on schooling. There is not some other way in which draft lottery numbers impact earnings. Now, we might be able to think of some. So maybe even being born on a certain day leads to earnings for reasons that have nothing to do with schooling. That would mean that draft lottery numbers impact earnings in a way that is not directly through schooling. So we want draft lottery numbers only to impact earnings through their effect on schooling and not to impact earnings in any other way. And that is referred to exclusion restriction. Other paths for lottery numbers to affect earnings are excluded. And this exclusion restriction language comes up a lot in econometrics and data science. So it's essentially we're using a proxy or an instrument, and we're assuming it only impacts our outcome variable through the variable that we're proxying for. So key results from their paper, they find that just using OLS, you get negative 5.9% return to schooling. And with two-stage least squares, you actually get negative 6.6%. Actually, have to, oh no, those are not negative. Sorry. I was like, wait, what? Tilde 5.9%. So about 5.9%, about 6.6%. I was like, ugh, that's bad. But yes, those are positive numbers, approximately those numbers. So the IV estimate is slightly higher than OLS, suggesting that OLS may underestimate the returns, possibly due to measurement error dominating ability bias. So we could have measurement error because measurement error, remember, is an endogeneity issue too. And so ability bias would downward bias our impact on returns to schooling because those high ability people, look, I have high ability, I'm already going to make high earnings. So then that's going to create too high of an OLS estimate. But clearly from this, we don't see too high of an estimate. Well, another reason that schooling could underestimate returns, as we've seen before, and as this exact example, is if we're using education, or sorry, we're really using schooling as a measure of fundamentally education, right? That's what we really believe affects earnings. So we already saw that measurement error in our previous lectures about endogeny will downward bias the OLS. So that's why the measurement error is dominating the ability bias. And that's what Angrist and Krueger chalk this up to, because ability bias we would expect the opposite change in these results. So finally, they do this robustness check because they want to know, okay, if a veteran status is, sorry, of course, I'm going to fix my typo right here. Where is it? I can't even find it. Yeah, this should be a $sign. A little collab markup lesson, maybe. And this should be a $sign. Oh, and we did have parentheses. Sorry, this is a huge waste of everybody's time. But look, gamma looks better now, so it was totally worth it. So robustness checks, right now we're going to take a look at, are we really decoupling schooling and veteran status? Because again, above we mentioned that maybe veteran status impacts earnings, and maybe being drafted has an impact on your earnings itself. So if what we really want to identify is whether schooling, so what we really want to identify is just the effect of schooling. We're using this strategy that also might be correlated with being a veteran. And so we kind of want to check, are we picking up the impact of being a veteran? So they do a robustness check and show, look, even if we vary this theta parameter, which is essentially the effect of being a veteran, we still get the same result on schooling. So how does our schooling coefficient change when we change our veteran parameter. If it changes a lot, then that's an issue because that means some of the veteran parameter is spilling into the spilling into the schooling. But if we don't see that, if we see there's no relationship here, so this theta parameter has no impact on rho, our rho hat, our estimate of the return to schooling, that would be a good sign. So this is just a robustness check they do, and I'll show you because I'm going to simulate this paper basically, and then we will see how this might have an impact. So first of all, I'm just going to kind of broadly walk you through the simulation. So basically, we are creating birth dates within these years. And then, so individualist cohort is going to be some cohort within those years. And then the cohorts are just a year. So a year is a cohort. And now we're going to have birthdays within cohorts, which is just 1 through 366 because we include leap years. And then one lottery per cohort because each year basically gets its own lottery. And so we're going to pick numbers 1 through 366. So that is literally the lottery number. And those are chosen randomly. So like if randomly so the way it actually worked is like they basically imagine Powerball and then they pull a number out and it says 250. Then they go over to say, okay, the first number we picked was 250. So anybody born on the 250th day of the year gets a lottery number of 1. That's a really bad lottery number because almost certainly when they randomly draw the maximum lottery number, 1 will be below it if they draft anybody. So basically, the only way you're not getting drafted is if you get a 1 is if they don't draft anybody, because that's the first group of people drafted. So that's how these work. So we're just randomly creating those right now. We're basically creating a bunch of birth dates for people in our sample. And now we have controls. Our control variables in our case are just going to be dummies. Well, Angrist and Krueger had more demographic information, but we're simulating people, so they don't vary for demographic reasons on our simulation. And then we have to create draft risk thresholds because it's like, okay, if you have low numbers, then you're high risk. If you have high numbers, then you're low risk. And so this is a matter of just creating those 2 risk levels of thresholds that are similar to what they do in the paper. And now we have our draft risk times cohort, because if you have a low risk, then you multiply by cohort. So that's going to be a schooling specific IV. And then we're going to have a veteran specific one too, because those medium risk people, that should start to mix in like who actually becomes a veteran. Low risk people should have more schooling, but less likely to be a veteran. So that's a little bit of the logic for why we're breaking those apart. Now we need to create, so this is just the raw data up here. Now we have to create data. As you've seen in the past, when we simulate these things, we have to simulate in a very specific order to sort of make the endogeneity problem real. Now, right here, we can see our source of endogeneity because we basically created ability above. And now ability is going to impact the years of schooling. That's going to create our endogeneity issue. Okay. And that's going to be uncorrelated, of course, with the probability of being drafted. So this just shows that if we ignore the endogeneity issue, we're going to get the wrong result because we can just do simple OLS, totally forget that we're doing the lottery draft thing at all. This is going to be the issue in that basically problem. You could even think of this as a missing variable bias type thing, because if we could actually just get data on ability, we could directly control for this problem. But because we never really observe ability, that's something that's very difficult to observe for selection into schooling. It's easier in general to find some random event like a draft lottery that caused people to select into schooling. So that's the underlying logic. Here is where we create our endogeneity issue for using OLS in this thing. And that's where we're just using ability bias there, basically. So earnings, so now we're going to create our truth is going to be 0.07 is the causal return to schooling in my simulation. And then the effect of veteran status is going to have a negative impact on earnings in this simulation. You could play with those if you want to see how this works or mess with this at all. So now down here, we're going to get our OLS versus two-stage least squares. We're just telling it what instruments to use and what variables to use. You can see that for yourself pretty easily. So let's go down to the results right here. So the true parameters, again, right here printed, 0.07 is the return to schooling. Negative 0.05 is the impact of earnings on being a veteran. So now we can see right here, schooling 0.29, that is much too big in our example. So ours is biased high upwards. Theirs was biased downwards, remember, but ours is biased upwards. That's because we've simulated the ability bias more than any measurement error issue. And that's why, because ability bias is going to lead to too big a return to schooling. Measurement error, namely using school as a proxy for education, will lead to too small an estimate of the impact of earnings on education. So which one of those dominates is an issue in their paper? It's not an issue in our simulation because we made ability bias the key factor. So here's our biased OLS coefficient on schooling. This is also a biased away from zero impact on veteran status. So both of those are biased results. Here we have negative 0.05. That is not inside this confidence interval. Our 0.07 is not inside this confidence interval. So now in our first 2LS, two-stage least square regression, we assume we're still using veteran as assuming veteran is exogenous. There we do get an unbiased result from assuming veteran is exogenous. And so that's okay. So what that tells us, we talked about smearing last time. The main reason veteran is so wrong here is not because there's anything wrong with the veteran variable, but because the endogeneity issue with the schooling variable is causing our estimate of the veteran variable to be biased. That's called smearing. The endogeneity issue in schooling is poisoning essentially the entire regression. Here, we get a better, of course, impact of schooling, and now, or sorry, veteran status, because that one is exogenous, and we're still treating it as exogenous here. Now we get a much better estimate of schooling. The true impact is, in fact, now inside our confidence interval. Now, in this second stage one, we treat both veteran status and schooling as endogenous. And here we go. Notice the veteran status got a little bit better in this case, a little bit closer to negative 0.05. Schooling also got a little bit closer to 0.07 in this regression because there is a little bit of an endogeneity issue worked into the veteran status. That's why they get a little bit better right here. Our schooling one got pretty good, and our treating veteran status as exogenous was pretty close to the truth. But we see we get even better when we do the truly correct regression. Now, finally, I mentioned this robustness check where we kind of want to check. Let's make an assumption about the effect of being a veteran. So we can vary that from negative 0.3 to 0.3. And then we can ask, okay, well, how does that impact our estimated return to schooling? Well, that actually appears to impact it a lot. When veteran status has a very negative impact, our return to schooling is much too high. Because remember, the truth is right here, 0.07. 0.25 is way too high. Similarly, when veteran status has a big impact on the return to schooling, our estimate of the return to schooling is way too low. Sorry. When veteran status has a very big impact on earnings, then our return to schooling is way too low. This is what would be expected in a problematic case where veteran status and schooling are very correlated because through the draft lottery. The draft lottery impacts both your choice to go to school and your earnings. And then, of course, those are both impacted by the draft lottery itself. So this is actually problematic for us that there's a big impact here. Now, this is a simulation. So I simulated this problem. Now I did and then here's just this is basically just says what I talked about and then gives a little bit more detail about what this p gamma or rho gamma plot is doing. So now what I did is I just simulated our, let's find where we're at, where we're creating our, so now we basically just changed this section of the data generating process to reduce that dependency a little bit. It's not obvious in their data. They have observational data, so it's not obvious when they collect their data what's happening here, but they are able to make this plot. And so in their example, they get a plot. So these results look very similar. So OLS, return to schooling is closer here because now we separated. So it's still biased upwards, but now we separated veteran status and schooling in a way that made this coefficient a little bit better. Still, the truth is still not in this confidence interval. Here, now we're getting even closer to 0.07 because this issue that we've decoupled veteran status and schooling more in this, that's even making two-stage least squares work a little bit better already. Here's our schooling again. That's right at 0.07 now, almost exactly 0.07, rounds to 0.07. So it's getting closer. And now this plot, now this is an upward sloping plot. So clearly that relationship changed. It's worth thinking about why that relationship changed. Importantly, though, this is basically an insignificant relationship if you look at the y-axis now. These are tiny numbers compared to what we were getting before versus this range of the input of veteran premium assumed is just as big as before. So we've alleviated this issue of potentially picking up veteran status in our instrument of schooling. Those could be too tightly correlated, and we're really picking up the impact of veteran status. How to assess that would be, okay, let's put in different assumed veteran statuses, see how that impacts our estimate to schooling. Cool. So that's just a nice robustness check. Those are, because often we've found, well, we don't really know after the fact because most of our reasoning is theoretical. Well, people who have a higher risk of being drafted should be incentivized to go to more schooling. That's a theoretical reason. Now we could kind of assess that a bit in the data, but we don't know if we've completely satisfied things like the exclusion restriction. These are some examples. This plot is one example of many sort of post-estimation techniques to try to assess, well, what would have happened in these different scenarios? Up here, bad things would have happened because there's a strong relationship between our assumed veteran premium and the estimates we're getting for schooling. Here, things look less problematic because there's a weak relationship between the assumed veteran premium, what happens to earnings from veteran, and our returns to schooling, making us more confident in our identification of the returns to schooling. All right. So thank you very much for that. I know some of you are thinking about endogeneity for your projects. So thinking about post-estimation techniques you might use. On that, I'll close on the same thing. Please reach out to me about your project so we can brainstorm, talk about different things, especially if we haven't talked about it in a while. And I look forward to seeing you. Bye-bye.